was like looking at the schedule classes for next year. Is your Chem 2 class in this class?
No,
Where's it?
my Kim class should be here in one of these rooms.
It says LAN.
That's so this building used to be called Landing.
Oh, okay, so it's still here.
Yes.
Okay, perfect. I was looking at it, I was like, I'm not really sure where that is.
No, that it'll still be here.
Okay, okay. I have to do my schedule on Monday, so I was like looking at it, trying to figure out where all my classes are.
I understand entirely.
Okay.
Okay, folks, it's that time of the morning, so I'm gonna go ahead and get started. So we have a very busy day ahead of us today. Because we have a lot that needs to be covered over the time frame of class and lab today. So the first question is the same question I asked the week before, fall break, about lab. Today is the last of the lab lectures. From then on, it'll be strictly be in the lab and doing experiments. So Zoom or no Zoom? Meaning, do we meet in person? I will find a classroom if we decide to do that. Or do we meet on Zoom? So, all those that would rather us meet on Zoom and not have to be in a classroom, raise your hands. That is the majority. So we will be on Zoom again for lab. It will be the exact same Zoom that I have for classes. So it won't be anything different other than the link we used last time. Okay, so that takes care of the first part. The next part, I've gotten a few emails about grades because you checked your grade after I gave back the exams on Tuesday, and then on the same day they dropped. I wanted to explain what was going on. So as I said Tuesday, I needed to go in and actually build this past week or this week of information. And when I built this week of information, it included 2 lab grades, which that's 50 points. It included 4 math, chemistry, and puzzles, that's 20 points. So right there's 70 points that all of a sudden the system is taking into account. So as we finish up the Lewis structures, and as we finish up the, as you complete those assignments, the Ed puzzle and the ones associated with the SEPR theory, as you complete those assignments, the grades will go back up. It's simply because all of a sudden it started taking into account all the grades instead of including the ones where you have a 0 right now because they haven't been filled in. So I wanted to let you know that's why it dropped. Basically, as soon as a column gets added in, it tends to drop a little bit and then go back up once you complete that assignment. So I wanted to explain that. And as far as labs, I'd hope to have both of your labs graded. I'll probably have one graded by the time lab starts today, but the other one I'm still stuck grading. That is because thankfully, and I'm excited about the reason I didn't get them graded, I had people coming to visit me the last 2 days, asking me questions, whether it was about the test or whether it was about a homework or whether it was, and I have 2 different classes. I have this class and another class. So I had a lot of students coming to my office. So, you know, I didn't get it graded, but I'm happy for the reason I was unable to grade it because I actually had people visiting me. And that makes me happy because I like to help the students one-on-one. And so I will get them to you. And then my goal is to try to get everything up to date this weekend. I mean, I'm almost there. I got one lab left to grade almost. Well, 1.5. So I'm almost there. But That's the reason I don't have your labs finished and ready for you today, is because I am happy to say I had people asking me questions. So, any questions for me so far? I try to respond to all of your questions so that you know those answers. And when I get multiple questions of the same type. Oh, and I did get one question about one of the ed puzzles. I fixed it, so that's done. I did get the ed puzzle graded that you had to type in answers for, so that grade's there now. So I've been doing some things, it's just a little slow going. Any questions for me? Okay, so today is going to be a busy day. Today's information, along with what I started on Tuesday, is information that is absolutely critical that you understand. To explain why, what we are doing today is we are talking about Lewis structures. We'll continue with that topic in class. And then in lab, we're going to be talking about BSEPR theory, valence bond theory, and molecular polarity. Now, the reason it is critical that you understand this information. When you begin College Chem 2, the very first chapter talks about intermolecular forces. And you cannot understand intermolecular forces if you don't understand molecule polarity. If you don't understand how the atoms are connected in a molecule from Lewis structures, you will not get intermolecular forces. It'll be a guess job. Lewis structures are important when you take organic chemistry, because we tend to use, now we tend to go from writing every element out to using an abbreviated version, which I will introduce to you just in case you run into it in the homework. But the entire point is you're going to have to understand these geometries to understand some of the things that happen with respect to organic reactions. So this is like a building block of a lot of chemistry. And so understanding it is important. So what we're going to do today, as I said, is this morning we're going to focus on Lewis structures. With respect to Lewis structures, I introduced the Lewis structure of an atom of an element on Tuesday. I introduced the Lewis structure of an ionic compound on Tuesday. And we started doing Lewis structures of very simple organic or covalent molecules on Tuesday. Today, we are going to start getting more complex with those Lewis structures. In doing so, we're going to talk about expanded octets. We're going to talk about formal charges. We're going to talk about resonance structures. So all of that is how we're going to build upon the foundation. And then again, we're going to apply these, getting the Lewis structures down. That is the foundation of being able to determine Vesper theory, being able to determine valence bond theory, and so on. Got to have the Lewis structure first. So let's get started. The very first thing I want to do is I'm going to just get our brains working back up. Hopefully with the homework, they're not too asleep, but we are going to do one simple organic compound. Then we're going to get into more complex compounds after that. So the first one we're going to do is going to be
Dichloromethane. And I will be using the guide I gave you. If you weren't here, you can pick up one at the end of class, but I will be using this guide so that if you wanted to follow along, you'd be able to. In fact, who did not get one that wants one? Oh, let me just pass them out so that you have them. Anybody else need packets? I think that's my packet that's left, so that should be right. Okay. So the very first thing we need to do is we need to total up the total number of valence electrons. We have one carbon atom, we have two hydrogen atoms, and we have two chlorines. As discussed on Tuesday, the number of valence electrons for your main group elements is equivalent to the last digit of the group number. So carbon being in group 14, the last digit is a 4, so it has 4 valence electrons. Hydrogen being in group 1, its last digit is the 1, so it has 1 valence electron. And chlorine being in group 17, the last digit is a 7, so it has 7 valence electrons. The carbon therefore contributes 4, the hydrogen 2, and the chlorines 14, for a total of 20 valence electrons to be distributed. Now, the step number 2 says to develop the skeletal structure. Typically, the least electronegative atom is going to be the central atom. Hydrogen, though, will never be in the center. And the other thing I told you is that carbon will always be the center of attention. So our carbon is going to be the central atom around which we're going to surround it with the other 4 elements. Now, it really does not matter what order you place these 4 elements in, but I will say when we get into Vesper theory and molecule polarity, it really does help if like elements are on the same side. So I tend to put them there just because it's going to help with respect to seeing molecule polarity. Now, step number 3 says to draw a single bond between the external atoms and the central atom. Remember, each of these lines represents 2 dots or 2 electrons. So we drew 4 lines, 4 times 2 is 8. So we'll be subtracting 8 electrons out from for our bonds, leaving us a total of 12 valence electrons still to distribute. The next piece says to distribute the remaining valence electrons around the external atoms, giving the external atoms an octet. You typically start with the most electronegative because they love their electrons. So we're going to give our chlorines 6 more electrons, because once we give them 6 more electrons, along with the 2 that they have in the bond, they now have an octet. And we'll do the same with the other chlorine. So in order to give our chlorines their octet, we use up the 12 electrons that we have and we hit 0. When you hit 0, you have to ask, does everybody have an octet? Your chlorines do, because you just gave them 6 electrons along with the 2 in their bond to give them a total of 8. Your carbon also has an octet because it has 8 within the 4 bonds that surround it. And your hydrogen only requires 2, so it too has its octet. So this is the Lewis dot structure for dichloromethane. Any questions? Brains woken up yet? Okay. Now we're going to add something to it that makes it a little bit more complicated, but not much. What we're going to do next is we're going to develop the Lewis structure of an ion. And we're going to keep this one simple. Let's do the Lewis dot structure of the hydronium ion. When you get into acid-base chemistry, hydronium is extremely important. Now, we begin the same way. We have 3 hydrogens and 1 oxygen. Hydrogen is in group 1, last digit of 1, so it has 1 valence electron. Oxygen is in group 16, the last digit of 6, so it has 6 valence electrons. The hydrogens give 3, the oxygen gives 6, for a total of 9 valence electrons. But here is the new piece. If you look at the second bullet point under step 1, you will notice that if you have a charge, you have to take into account the charge. Because we have a positively charged species, it means there's fewer electrons. So we need to subtract out 1 electron because we have a +1 charge due to the charge. Meaning we actually only have 8 electrons to distribute around the molecule. Now we need to develop our skeletal structure. The skeletal structure is going to have oxygen in the middle because hydrogen is never in the middle, surrounded by our 3 hydrogen atoms. You then draw a single bond between the external atom and the central atom. Each of those bonds represents 2 electrons, so you subtract out 2 electrons for each bond. 2 times 3 is 6, so we'll subtract out 6 electrons due to our bonds. And that still gives us 2. We are on step 3, bullet point 2, where we distribute the remaining valence electrons around the external atoms, giving the external atoms an octet. Well, our hydrogens only require 2. So all of our hydrogens have their octet. So now we move to step 3, bullet point 3. If valence electrons still remain, we're going to place them on the central atom in pairs. Since we still have 2 valence electrons, we have to place them on the central atom in pairs. We'll subtract out those 2 electrons, and now we've hit 0. It itself is an ion. Its bonds are not ionic because hydronium as a whole is a plus charge. So the hydronium, it's an ion, and then you would have to compare it with a negative ion in order to make it an ionic compound. So it's a little different. Right, but that was because we were dealing with ions of an atom. Now we're dealing with a polyatomic ion. Polyatomic ions, there are bonds within the ion itself, but again, it's the ion itself that is the ion, not just the elements. So the oxygen is not an ion. It's only an ion once you add the H3O plus all together. Does that make sense? Okay. Now, though, this is an ion. Oh, well, we needed to make sure everybody had an octet. Everybody has an octet because your hydrogens have 2 and the oxygen has 6 within the bonds and 2 within the lone pair. So it is, everybody has their octet. But now this is an ion, so we have to illustrate it as an ion. So we put the entire thing in brackets with the charge outside. Ions go in brackets with the charge outside as a superscript.
So you don't want to go to the discussion.
No, that is up to you. We haven't gotten to the VSEPR theory yet. And that's where the bond angles come in. So it's up to you whether you draw, I mean, I'll take a Lewis structure as long as you had the hydrogen single bonded to the oxygen and the lone pair on the oxygen and it in brackets with the charge. I'll take the Lewis structure however you give it to me, as long as it has those qualities. Let's look at another one. Let's look at the cyanide ion. So we have one carbon, we have one nitrogen. Carbon is in group 14, the last digit is a 4, so it has 4 valence electrons. The nitrogen's in group 15, the last digit of 5, so it has 5 valence electrons. The carbon contributes 4, the nitrogen 5, that's a total of 9 valence electrons. But this is a charged species, so if you look at bullet point 2, on step 1, you will see that for an anion, you have to add the number of electrons indicated by the charge. Since this is a -1, that means we're going to add 1 electron due to the charge, meaning we actually have 10 electrons that we're going to have to distribute around our molecule. Now, in this particular case, you've only got 2 atoms, so neither one of them is really the central atom. There's only one way that you can put them, and that's side by side or up and down. I mean, we are going to go on to step number 3 though, and we are going to draw a single bond between the outer atom and the central atom. We'll subtract 2 for the bond we drew, leaving us 8 valence electrons still to distribute. The next thing says to give your external atoms an octet. And you always want the most electronegative. The most electronegative is the nitrogen. So you're going to give your nitrogen its octet first. And when you give the nitrogen an octet, that means you add 6 additional electrons. And you still have 2 left to go. Those 2 are going to get placed on your carbon atom. And we hit 0. When you hit 0, you say, does everybody have an octet? The answer is no. Your nitrogen does, because it has 6 electrons in the lone pair and it has 2 electrons in the bond. But your carbon currently only has 4 because it has 2 in the bond and 2 lone pair. Because we do not have an octet on carbon, that means that we have to share electrons. Because remember, once you hit 0, you cannot add lines, you cannot add dots. All you can do is rearrange what's already there. So we're going to share a pair of electrons. And when you share a pair of electrons, you get a double bond. And we have this structure that emerges. When this structure emerges, you ask, does everybody have an octet? Your nitrogen still has an octet. It has 4 within the lone pairs and it has 4 in the bonds for a total of 8. But your carbon currently does not have an octet because it only has 4 within the bonds and 2 in lone pairs, making 6. Because carbon does not have an octet, we have to share another pair of electrons between the 2 atomic nuclei. And the structure that emerges is this structure. Because we altered the structure, we asked, does everybody have an octet? Your nitrogen does have an octet because it has 6 within the triple bond and it has 2 in the lone pair. Your carbon has an octet because it has 6 within the triple bond and 2 within the lone pair. So yes, everybody has an octet. So to finish this structure, we're going to place that ion in brackets with the charge outside. Questions? Okay. So now the next thing we're going to get into is what is called an expanded octet. what you need to know regarding this is that the maximum number of electrons for a period 2 non-metal or metalloid is 8. It cannot go past an octet. But the number of electrons allowed on a period 3 through 7 non-metal and metalloid can, it doesn't have to be, but it can be greater than 8 because of the availability of the D subshell. It does not mean that we have any electrons in the D yet, but the D is there. As soon as you open up principal quantum number 3, you have the 3s, the 3p, and the 3d. Whether there's electrons in them or not, doesn't matter. As soon as you open it up, you have all of those subshells available. And because that D subshell is available, you can have an expanded octet. So the question is, do we need to expand our octet? Because remember, I said, I specifically said that it can be greater, doesn't have to be. So the question is, do we? The answer is yes, if you can minimize formal charge. Now, technically, folks, you can calculate the formal charge for any element, but it is critical that when you're thinking about Lewis structures, that you always think about formal charge when you get to period 3 or greater. So let's talk formal charge. If you look at the somewhere, page 2, step 6, I've talked about formal charge. Okay, so that is where we have elements that actually have electrons in the D. But the D is available starting in period 3. Because remember the principal quantum number is 3. And so you have 3s, 3p, and 3d. You don't have any elements with electrons in the 3d until you get to period 4, but you still have it available starting in period 3. So formal charge of an element is going to be equal to that element's valence electrons minus 1 for every bond plus 1 for every dot. Which you see you've got the equation on this sheet. Now, formal charge is minimized when the FC is as close to 0 as possible. We know that it is valid. When the most electronegative atom gets the formal charge, gets the negative formal charge. And finally, we know that we have got the right structure when you do not have like signs or same sign formal charges on adjacent atoms. And the reason for this last one is basically you don't want to bring a negative and a negative close to one another because a negative and a negative would repulse. You can't bring a positive and a positive close to one another because a positive and a positive would repulse. So you always have to make sure that you have a positive and a negative close beside each other if you've got to have formal charges on adjacent atoms. And again, this is all written in number 6. I just wrote it out since you may wind up rewatching this video. I wanted to go ahead and write it out. So let's look at some. Let's look at some of these. The first one I would look at, let's see. Who do I want to go to first? Trying to think so that I don't actually, let's go with something straightforward. Sulfur trioxide. I'm trying not to get into resonance yet. That's the problem. Sulfur trioxide. We have 1 sulfur and 3 oxygens. Sulfur is in group 16. The last digit is the 6, so it has 6 valence electrons. We have oxygen. Oxygen is in group 16. The last digit is 6, so it has 6 valence electrons. So the sulfur contributes 6, the oxygen's 18 for a total of 24 valence electrons to distribute. Step number 2 is to arrange the skeletal structure. The least electronegative atom will go in the center, and it's typically the first element listed. So we're going to place the sulfur in the center and surround it with our oxygen atoms. The next step, step 3, says to start by drawing a single bond between your outer atoms and your central atom. You will subtract 2 for each bond you draw. We drew 3 bonds. 3 times 2 is 6. So we'll be subtracting out 6 electrons due to our bonds, leaving 18 valence electrons still to distribute. The second bullet under step 3 says to give your outer atoms an octet. So to give each oxygen an octet, each oxygen is going to need an additional 6 valence electrons. It needs 6 because that way it has 6 within the lone pair and 2 within the bond to make 8. Now, in giving each of our oxygens an octet, we've used up our 18 valence electrons, so we hit 0. The next step says, does everybody have an octet? Your oxygens do, but your sulfur does not. So we're going to share a pair of electrons in between our oxygen and our sulfur. And no, it does not matter where you start. I'm right-handed, so I'll be honest, I have a tendency to start with the right one. Okay, so when we do so, we get this structure. And we asked, does everybody have an octet? And once I finish drawing this structure, you will see that yes, everybody does have an octet because all of the oxygen atoms have 8. The 2 that are single bonded have 6 in the lone pair and 2 in the single bond. The one that is double bonded has 4 in the lone pair and 4 in the double bond. So yes, all of the oxygens have an octet, but so does sulfur because it has 4 bonds surrounding it. That's 8 electrons. Now here's where formal charge comes in because sulfur is in period 3. So that's when we have to deal with our formal charges. Now, to calculate the formal charge on our sulfur is going to be equal to the sulfur's valence electrons. I am now using the formula on page 2. It's going to be equal to the sulfur's valence electrons, which is 6, minus 1 for every bond. On that sulfur, we have 4 bonds. And 1 for every dot, which there are none. So right now, our sulfur has a +2 formal charge. We can calculate the formal charge of our single bonded oxygens. Because they look identical, I'm only going to calculate it once, but I am indicating that this is for the singles. It has 6 valence electrons. It has 1 bond and it has 6 lone electrons, 6 dots. So the formal charge on our oxygen, single bond oxygens are both a -1. So this one has a formal charge equal to a -1 and this one has a formal charge equal to a -1. The formal charge on our double bonded oxygen is equal to 6 electrons minus 1 for every bond. It has 2 bonds and 1 for every lone electron. It has 4, so that has a formal charge of 0. So right now, our absolute value of formal charge equals 4 because you don't take into account signs when you're talking absolute value. That's a high formal charge. Again, you don't take into account the signs, you just look at the numerical values when you're taking an absolute value. So 2 plus 1 plus 1, that's 4. Any questions about that? So this is a bad structure. You want to minimize formal charge. We want to get them as close to 0 as possible. So you will take a pair of electrons from a negative formal charge and share them with a positive formal charge. You will take a pair of electrons from a negative formal charge and share them with a positive formal charge. When we do so, this structure arises. So let's calculate formal charges again. So formal charge of our sulfur, we have 6 valence electrons minus 1 for every bond. It now has 5 bonds on it, plus 1 for every dot. It still has 0 dots. So it's down to a plus 1 formal charge. For our single bonded oxygen, it's 6 valence electrons minus 1 for every bond, plus 1 for every lone electron, so 1 and 6 respectively. So it still has a negative 1 formal charge. And for our double bonded oxygens, it's going to be equal to 6 valence electrons minus 1 for every bond, it's 2, plus 1 for every lone electron, that's 4, leaving those with a formal charge of 0. So now our absolute value of formal charge is reduced to 2. That's better. But the question is, can we reduce it further? Can we get it closer to 0? Because 0 is our goal. And the answer is yes, you can. You can share one more set of electrons from a negative formal charge to a plus formal charge. And the structure that emerges when you do so is this structure. Looking at our formal charge of sulfur, that is 6 valence electrons minus 1 for every bond. The sulfur now has 6 bonds plus 1 for every dot. It still has no dots, but now the formal charge on that sulfur is equal to 0. For our double bonded oxygens, because they're all the same, I only do it once. That's 6 valence electrons minus 1 for every bond. It has 2 plus 1 for every lone electron, which is 4, giving those also a formal charge of 0. So now we have actually reduced the absolute value of formal charge to 0. This is the structure of sulfur trioxide. Sulfur has an expanded octet, and it is allowed to do so because it is in period 3 or greater. Any questions about that? You always want the absolute value to be as low as possible. Now, I will say, and I pointed it out when I was talking about, it would be the first bullet point under the formula on page of step 6. If you have an ion, like sulfate, which we'll do in a moment, the formal charge will have to come out equal to the charge on the ion. But if it's a neutral compound, you can usually get it to 0. It's not always a possibility. I'll show you one. I'll show you an example once we talk about the next topic. Questions? Okay, so let's move on to the last piece of new information. And that is resonance. Resonance structures exist when you make a choice as to who makes the multiple bond, but you could have made an equivalent choice. Resonance structures exist when you make a choice as to who can make a multiple bond with the central atom, but you could have made an equivalent choice. One more time. Resonance structures exist when you make a choice as to who makes the multiple bond with the central atom, but you could have made an equivalent choice. Let me show you what I mean. And to do so, I am going to use ozone to start. Ozone is O3. There are 3 oxygen atoms. Oxygen is in group 16. The last digit is a 6, so it has 6 valence electrons. 3 oxygens times 6 valence electrons means we're going to have 18 valence electrons to distribute throughout our molecule. When you have 3 of the same atom, it doesn't matter who is the central atom. You're just going to pick one of them and put the other 2 around it. To get to the skeletal structure. The next step says to draw a single bond between the outer atom and the central atom. And you're going to subtract 2 for each bond you drew. We drew 2 bonds. 2 times 2 is 4. So we'll subtract out 4 electrons due to our bonds, giving us a total of 14 still to distribute. The next piece says to give your outer atoms an octet. To give our outer atoms an octet, we need to distribute 6 more electrons on each of the outer oxygens. That way it has 6 in the lone pair and 2 in the bond, giving it a total of 8. To give both of our oxygens their octet, we used an additional 12 on our outer atoms, and we're left with 2. According to our step-by-step rules, if any still remain, they go on the central atom in pairs. So our last 2 will go on our central atom in pairs. And you ask, does everybody have an octet? Your outer atoms, they have their 8 valence electrons. But your central oxygen currently only has 2 in the lone pair and 4 in each bond, or 4 total in the bonds, for a total of 6 valence electrons. So no, not everybody has an octet. Because not everybody has an octet, we have got to share electrons. Because we need to make an octet. When we share that pair of electrons, we ask, does everybody have an octet? Our single bonded oxygen does have 8 valence electrons because it has 6 in the lone pairs and 2 in the single bond. Our double bonded oxygen on the right has 8 valence electrons. It has 4 in the lone pairs and 4 in the double bond. And our central atom has an octet because it has 8 valence electrons, 6 within the bonds and 2 in the lone pair. So at this point, everybody has an octet. But here is where that statement I made about resonance structures came in. I made a choice that the right-hand oxygen was going to share its electrons. I could have made the equivalent choice and made it instead of the right. I could have said, okay, let's make the left-hand one share the electrons. And if the left-hand one shared the electrons, then this structure would have emerged. These are resonance structures. To illustrate that they are resonance structures, we use a double-headed arrow. So the double-headed arrow divides 2 resonance structures, or 2 or more, I should say. We use the double-headed arrow. Basically, folks, when you get a resonance structure, what it really means is that the structure is neither one of these, it's somewhere in between. It's not the top one, it's not the bottom one, it's actually something in between the two. So this is an example of when you make a choice and you could have made an equivalent choice, then you have to draw resonance structures. And yes, you have to draw all of the possible resonance structures. In this case, there were only 2. I will let you know, most of your polyatomic ions that are oxy ions, so sulfate, nitrate, perchlorate, those are all going to be resonance structures. So if you see a polyatomic ion that's an oxy ion, you can pretty much guarantee you're going to have resonance. So that could be one of your cues that, oh, I better draw some more structures. Okay, let's look at another example. And this one's actually an interesting one to try to do. N2O can technically have 3 resonance structures. But one of them is better than the others. N2O, you can have this structure. You can have this structure. or you can have this structure. But one of these is better than the others. To figure out which one's better, use your formal charges. So in this one, we can do formal charge of our oxygen. It's going to have 6 valence electrons minus 1 for every bond. It has 1 plus 1 for every lone electron. It has 6. That gives it a total of a -1 formal charge. For our central nitrogen, it is going to be 5 valence electrons minus 1 for every bond. It has 4 plus 1 for every lone electron. It has 0, so that gives it a +1 formal charge. For our left-hand nitrogen or external nitrogen, it's 5 for minus 1 for every bond. It has 3 plus 1 for every lone electron. It has 2, giving it a formal charge of 0. For our middle structure, the formal charge on our oxygen is equal to 6 valence electrons minus 1 for every bond. It has 2 bonds plus 1 for every lone electron. It has 4, giving it a formal charge of 0. Our nitrogen, center nitrogen, it's going to be 5 valence electrons minus 1 for every bond. It has 4 bonds plus 1 for every lone electron. It has 0, so it has a +1 formal charge. For our external nitrogen, it has 5 valence electrons minus 1 for every bond. It has 2 bonds plus 1 for every lone electron. It has 4, giving it a -1 formal charge. Now for the structure on the far right. You have formal charge on your oxygen. It has 1 for every bond. 6 minus 1 for every bond. It has 3 bonds plus 1 for every lone electron. It now has a +1 formal charge. For the middle nitrogen, it is 5 valence electrons minus 1 for every bond. It's 4 plus 1 for every lone electron, which is 0, so it has a +1 formal charge. And for our external nitrogen, it has 5 valence electrons minus 1 for every bond. It has 1 bond plus 1 for every lone electron, which is 6, so it has a -2 formal charge. Upon inspection of formal charges, who goes away? The far right one is the worst. Why? 1, it has the highest overall formal charge. Another reason? They have like charges on adjacent atoms. And there's one more reason. What's the third reason? Oxygen should have the negative charge because it is more electronegative, according to the table on page 4. So that leaves us 2. One of them is still better than the other. Who's the best? It is the first one. Why? The most electronegative atom got the negative charge. And it has the lowest overall charge. It has one of the lowest overall formal charges. So you can have resonance structures. That does not mean that they're the best resonance structure in the world. Just means they are a resonance structure. Some resonance structures are definitely better than others. So let's look at one more that combines everything. We're going to look at sulfate, which will probably take the last 12 minutes of class. It's a long one. What in the?
Okay. I don't know how, but okay. That's okay. I'll deal.
Okay, so sulfate. You have 1 sulfur, 4 oxygens. Both are in group 16. Last digit is 6, so they each have 6 valence electrons. The sulfur contributes 6. The oxygens contribute 24 for a total of 30. But you do have to take into account the charge, and since it's a negative 2 charge, it means we're going to add 2 electrons because it is negative, because that means there's excess electrons. So we actually have 32 electrons to distribute. The sulfur atom is going to be our central atom around which we're going to place all of our oxygens. We then draw a single bond between the outer atoms of the central atom and subtract 2 for each bond we drew. We drew 4 bonds. 4 times 2 is 8. So we'll subtract out 8 due to our bonds, leaving us 24 valence electrons still to distribute. The next step says to give your outer atoms an octet. We give each of our outer atoms an octet by giving them 6 additional electrons. When you give each of the oxygens 6 additional electrons, you use up the last of the 24 in the outer atoms, and you are left at 0. When you hit 0, you should ask, does everybody have an octet? At this point, yes, everybody has an octet because everybody has 8 valence electrons. But is that sufficient here? No, why? Because sulfur's in period 3 through 7, so we got to figure out if we need an expanded octet. So we do formal charges. Formal charge of our sulfur is equal to 6 valence electrons minus 1 for every bond. It has 4 bonds plus 1 for every lone electron. It has none. So that equals a +2. So right now this sulfur is going to have a +2 formal charge. The oxygens are all the same, so we only have to do this once. Formal charge of oxygen, 6 minus. It has 1 bond plus 6 electrons, so all of our oxygens have a -1 formal charge. So there, if you were to take in the absolute value of our formal charge, which I'm not going to write out the word, I'm just going to use the symbol for absolute value, which is the larger lines. We do the absolute value of our formal charge, it's equal to 6. That's a whole lot of formal charge going on. So we do need to minimize this. We minimize by sharing a pair of electrons between an external atom and a central atom. When we share a pair of electrons, the structure that emerges with the ones I shared is this structure. Now, folks, one thing I did not say, which because I wanted you to get used to calculating formal charge, is if you don't change the atom, its formal charge doesn't change. So because I didn't change those 3 single bonded oxygens in any way, their formal charge is going to remain the same. So I really don't have to go back and calculate the formal charge of all of these because I've already done it once. Again, what it boils down to is if the formal charge is not going to change unless you change the bonding. So I only need to calculate the formal charge of my sulfur. Formal charge of the sulfur is 6 valence electrons minus 1 for every bond. It has 5 plus 1 for every lone electron. It has 0. So it now has a plus one formal charge. And our double bonded oxygen, it's going to be 6 valence electrons minus 1 for every bond. It has 2 plus 1 for every lone electron. It has 4. So that is equal to a 0 formal charge. So what we just did is we minimized, or we've started to minimize our formal charge, and we've got it down to 4 instead of 6. But we can still try to minimize it some more. By bringing in another pair of electrons. Now, this is where another something comes in that I haven't described. And that is chemistry likes symmetry. So if I'm going to bring in another pair of electrons, the one I want to do it with is going to be the right-hand side oxygen instead of the top or the bottom. I mean, the left-hand side oxygen instead of the top or the bottom. So the structure that emerges once I share that pair of electrons is this. Because we altered the structure, let's check formal charge again. The formal charge of our sulfur is going to be equal to 6 valence electrons minus 1 for every bond. It now has 6 bonds plus 1 for every lone electron, which is 0. So it now has a formal charge of 0. The 2 single bonds that we never have touched are still a -1. The oxygen that we did not touch between our second and third is still a 0. So we just need to check the oxygen that we touched. And that's 6 valence electrons minus 1 for every bond, which is 2, plus 1 for every lone electron, which is 4. So it now has a 0 formal charge as well. So we now minimize the formal charge down to 2. And you're not going to get any closer, because if you look at the statement under the formal charge equation, when you have an ion, the formal charge is going to be equal to the ion's charge. You can't get away from it. You can't get rid of all the formal charge. So one of our structures is going to be this structure. But because this is an ion, ions always go in brackets with the charge as a superscript. But this is not the only structure. I chose the right and left, but there's no reason I couldn't have chosen the top and the bottom. So that means I have to have a resonance structure. Hence, I draw the double bonded arrow. And my top and bottom get the double bond. And that is what you would draw for the Lewis structure of sulfate. Sulfate's nice, it only has 2. Carbonate, nitrate, they both have 3. Phosphate has 4. I can't remember how many perchlorate it has. I think it has 4. So you can get quite a few resonance structures that are valid resonance structures. Okay, yes.
So it's not a resonance structure if the formal charge is too high. It's only a resonance with the lowest formal charge.
You don't even think about whether or not it has a okay, that's actually the question. You don't think about whether it has a resonance structure until you get to the best Lewis structure. And then you say, could it have a resonance structure? So that's why I didn't even pay attention to it until I got to the very end and found the best resonance structure. And then I looked to see if it had additional Lewis structure that could be resonance.
For ozone, you had the one that had the higher formal charge.
Ozone,
Four.
you're talking about the N2O,
Oh, yeah.
nitrogen monoxide. I knew that one from off the top of my head. You can have resonance that's bad. I mean, I could have, technically, yes, the ones above these are resonance structures, but they're bad ones. So yes, you can, all of them are resonance structures because they're all, I did this when I could have done this, but that doesn't mean they're good ones. I just wanted to show you N2O because that shows you when you get to a bad resonance structure, why is a bad resonance structure. Okay, folks, what we will be doing this afternoon is we're going to be taking these Lewis structures and then we're going to be applying SCPR theory, which is valence shell electron pair repulsion theory. We're going to be applying valence bond theory or VD theory. And we're going to be talking about molecular polarity, but it's all going to be based off of these original Lewis structures. You can do some of it now if it just asks you to draw the Lewis structures. Now, and even the expanded octet, the ones you would have to wait for is if it asks you for the molecular geometry or valence bond. So you can do part of it now, but you can't do the other part until after lab lecture. Yes, I put a few problems of lab in it too. Unfortunately, it's a bit longer, because this stuff, again, is something you've got to know for the next courses in line. So I figured I better keep it. You need to more practice on it. And it is time to go. I will see some of you at 10:50 on Zoom, and I'll see the rest of you at 2:40 on.